Okay, welcome focused learners. Let's get right into it. I want you to imagine the Cambridge IGCSE Physics exam not as some terrifying, anxiety-inducing test, but as a high-security bank vault. Inside that vault, your top-tier grade. And today, we're putting together the ultimate crew to crack it. Specifically, we're targeting the deepest, most heavily guarded, and honestly, the most frequently misunderstood area of the entire syllabus, kinematics and graphs. Now, whether you're sitting the primary 0625 paper, or you're tackling the 0651, 0652, 5054, or even laying the foundations for the A-level 9702 variants, the strategy we're unpacking in this explainer is literally your master key. Let's take a look at two suspects who tried to crack this exact vault, and, well, they triggered every alarm in the building. First up, we've got Alex. If you look at Alex's paper, it is absolutely overloaded with raw physics facts. I mean, just brain dumping every single equation they've ever memorized right onto the page, but completely lacking any real analytical depth. And right beside Alex, we have Sam. Sam's problem? Rushing. Sam rushed the execution, completely missed the command word requirements, and fundamentally confused the graph types. You can see their flawed answers right here, just absolutely covered in red pen marks from the examiner. But don't worry, we're going to fix this. We're assembling a team of cognitive tools to pull off the perfect answer heist and transform every single one of those red marks into green check marks.
So, let's dive into this. Why is it that incredibly capable, intelligent students like Alex and Sam consistently drop such vital marks when they're faced with speed time graphs? Well, the answer actually lies straight in the Cambridge Principal Examiner reports. You see, students don't lose marks because they don't know what speed is or what time is. They lose marks because they rely on a superficial understanding rather than rigorous, step-by-step analytical depth. Think about it. When the clock is ticking and the tension is building, if you don't have a solid, unshakable system in place, you panic. Students see a sloping line and they instantly guess its meaning without even bothering to check the axes. They completely fail to execute the correct analytical framework. But today, right now, we are moving entirely away from guessing. We're going to deconstruct the exact mechanics of these graphs so that the next time you see one, you don't feel a drop of panic. You're just going to feel total, absolute control. We're going to diagnose the exact flaws in those red pen paragraphs, and we are going to rewrite them together.
To pull off this exam heist, we obviously need a flawless blueprint. So here is our sequence. We're hitting the kinematics trap first, then gradients and areas decoded, followed by acceleration, moving into the method mark strategy, and finishing up with the top examiner warnings. Let's move. All right, phase one of our blueprint, the kinematics trap, specifically confusing cause and effect. Let's step right into the very first major trap identified in those examiner reports. The examiners explicitly state that students routinely confuse cause and effect in kinematics graphs. Now, what does that mean? It's basically a trap of terminology and visual illusion. Students look at the shape of a line and they instantly assume a physical reality without verifying the parameters. Because, when you're under pressure, a straight diagonal line looks like a straight diagonal line, no matter what graph it's sitting on. Take a look at this comparison. We have distance time graphs on the left and speed time graphs on the right. Visually, they can look identical. A flat horizontal line on a distance time graph means the distance is not changing as time passes, right? So the object is completely stationary. It's parked. But take that exact same flat horizontal line and place it on a speed time graph, the object is moving. It just has a constant speed. Its speed isn't changing, but it is absolutely covering ground. Examiners note that candidates constantly confuse these two. They'll describe a stationary object when they're actually looking at a constant speed graph or vice versa. This is exactly what Sam did earlier. Sam rushed, saw a flat line, and just wrote "the car is parked" on a speed time graph. Lost all the marks. You literally have to train your eyes to immediately snap to the y-axis before you even look at the data trend. The axis labels dictate the entire reality of the problem.
Moving on to Section 2, Gradients and Areas Decoded. This is where we unlock your tools.
Okay, now that we know what the trap is, it's time to assemble our cognitive tools. Think of gradients and areas as your precision safecracking instruments. You can't just stare at a graph and hope the answer magically materializes in your brain. This brilliant matrix right here is your master decoder. Honestly, take a mental photograph of this table right now. If you're looking at a distance time graph, calculating the gradient, the change in y over the change in x, that gives you the speed. What about the area under a distance time graph? Not applicable in this syllabus. It doesn't give you a useful physical quantity, so just ignore it. But shift your attention to the speed time graph. If you calculate the gradient of a speed time graph, boom, you unlock the acceleration. And crucially, this is a big one, if you calculate the area under the line on a speed time graph, you determine the total distance traveled. Examiners explicitly test your ability to switch between these analytical frameworks. When an examiner asks for distance from a speed-time graph, they are specifically testing to see if you know to pull out your area calculation tool instead of your gradient calculation tool. It's a test of strategy, not just math.
Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to it. Let's look at this procedural framework. This right here is our PEAL framework, point, evidence, explanation, link, but we've adapted it specifically for physics calculations. Step 1, deconstruct the command word. Is the exam asking you to calculate, describe, or determine? They all mean different things. Step 2, extract the relevant data from the texts and the tables. Step 3, select your analytical framework. Like we just talked about, are we using the gradient tool or the area tool? Step 4, execute the analysis with incredibly clear step-by-step working. And finally, Step 5, present the final result with the absolutely correct terminology and units. When you structure your answers this way, those red marks instantly transform into green check marks. You're no longer just throwing raw physics facts at the page like Alex did, you're executing a highly targeted, evidence-based operation. Section 3, Acceleration and Velocity. This is all about the core equation. Let's shift to the heavyweight champion of the physics syllabus, calculating acceleration correctly. Listen, this is where examiners separate the top-tier candidates from everyone else. The theoretical foundation starts with this exact, precise definition. Acceleration is the change in velocity per unit time. The formula is A equals delta V over delta t, where that delta V is the change in velocity and delta t is the time taken. These precise definitions, they are the literal architecture of your success. If a question asks you to define acceleration, you cannot, I repeat, you cannot just write when something speeds up. You will get 0 marks. You must use the rigorous academic phrasing, change in velocity per unit time. This formula isn't just a random string of letters, it is a logical statement. It's telling you exactly how much faster or slower an object is getting every single second.
So how do we actually apply that formula to a visual graph? Well, you calculate acceleration directly from the gradient of a speed-time graph. Let's visualize this together. Your y-axis is speed, or velocity. Your x-axis is time. Now think back to math class. The formula for a gradient is the change in y divided by the change in x. So on this graph, that translates to the change in velocity divided by the time taken. It perfectly, flawlessly mirrors our core equation. Top students achieve those high grades by showing evidence-based reasoning, making this connection explicit. They don't just guess a number, they will literally draw a large triangle right there on the graph, read the coordinates incredibly clearly, and show the examiner exactly how they derive that change in y and change in x. They are actively proving their analytical depth. And that's how you show the examiner you aren't just reciting a textbook, but that you are truly reading the data.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to cracking this vault.
Phase 4, the method marks strategy. This is how we secure the vault.
Now, what's incredibly interesting about this phase is that it's all about guaranteeing your payload, even if disaster strikes. You see, the Cambridge assessment framework is fundamentally designed to reward logical, structured reasoning. The examiners actually want to give you marks, but you have to give them the evidence they need to do it. Here is a direct, blaring alarm straight from the principal examiner reports. Students lose marks simply by not showing their working. It is heartbreaking. Imagine doing all that hard cognitive work in your head, pressing the wrong button on your calculator and writing down a mathematically incorrect final answer. If you just write down that wrong answer, you get a 0, but if you wrote down the formula first, substituted the correct numbers from the graph, and then made a calculator error, method marks can save you. The examiner will look at your process and say, okay, this student totally understands the physics, they just made a silly clerical error, and they will award you the vast majority of the marks. Rushing students fail here every time because they treat the exam like a math sprint instead of a step-by-step physics demonstration.
Let's practice applying this to a complex data source right now. I want you to imagine a 60-second visual timer ticking down in your mind. Challenge 1, data scan. Step 1 is deconstruct. You have 60 seconds to extract the core trend from a complex chart. Identify exactly what given information you have. Challenge 2, solve systematically. Break the problem into highly logical steps. Write the formula. Substitute the extracted values. Calculate. And challenge 3, evaluate and check for reasonableness.
This right here is where you find the flaw. Look, if you just calculated the acceleration of a regular bicycle and your answer is 500 meters per second squared, you need to evaluate that. That is literally faster than a fighter jet taking off. Check for reasonableness. It means you probably multiplied when you were supposed to divide. This deconstruct, solve, evaluate cycle, it is your ultimate safety net.
Finally, we reach Section 5, Top Examiner Warnings. This is all about avoiding the lasers. To successfully navigate your way out of this exam vault with full marks, we absolutely have to avoid the laser tripwires. These are the specific repeated errors that Cambridge principal examiners compile every single year. So, the crucial point here is rapidly breaking down and neutralizing these three fatal flaws. Number 1. Confusing cause and effect in speed time graphs. We already neutralized this in Step 1 by promising to always check our axes. Number 2. Forgetting to check format and presentation. This means losing silly marks by forgetting your units, not using proper headings, or having incredibly messy, unreadable annotations scrawled on your graph. Keep it clean. Number 3. Answers are not specific to the context given. Look, if the question is specifically about a parachutist reaching terminal velocity, please don't give a generic, boring answer about an object. Mention air resistance. Mention the parachutist's weight. You need to hack your memory right now. Create a mnemonic using the first letters of key terms to lock this in. Axes, presentation, context. A, P, C. Always present context.
Now here is the real insider secret, the golden ticket that elevates an answer from just being good to being absolutely top tier. Principal examiner reports constantly highlight that candidates who reference cross-topic connections achieve significantly higher marks. When you are analyzing these graphs, you shouldn't just lock yourself in a little kinematics bubble. Use comparative analysis. Identify similarities and differences using comparative connectives like whereas, similarly, or in contrast. For example, if you see a curve on a graph where the gradient is clearly decreasing, connect that to forces. Explain that the decreasing acceleration on the speed-time graph indicates that the resultant force is also decreasing, perhaps due to increasing air resistance. By bridging kinematics and dynamics together like that, you prove to the examiner that you possess a comprehensive, integrated understanding of the entire physics syllabus. It's a brilliant move.
So let's recap our complete physics answering system with this standardized sequence. Imagine a progress bar showing your mark potential, and we are pushing it all the way to 100%. Step 1. Identify the key elements and fully decode those command words. Step 2. Apply the relevant principles, utilizing the Peel framework and our gradient area matrix. Step 3. Execute the analysis with crystal clear, methodical working to secure every single one of those method marks. Step 4. Verify your results by checking them for real-world physical reasonableness. Step 5. Present appropriately with precise terminology in the correct units. Students who systematically implement these exact physics strategies see an average improvement of 2 full grade boundaries. Seriously. But that transformation only happens if they practice consistently with our weekly explainers. You've got to put the reps in.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by without having the ultimate strategy blueprint right in your corner.
You now have the exact cognitive tools and the insider knowledge to pull off the perfect exam heist. But remember, knowledge actually requires action, so drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team reads and responds to every single comment to help you navigate your specific hurdles. Like and share this explainer with a study partner so you can hold each other accountable. Before you go, I want you to ask yourself, are you just memorizing equations, or are you actually learning to read the language of the physical universe? Ace the Exams, your Cambridge success starts here. Keep analyzing, keep calculating, and I'll see you in the next one.